All right, on page 59, we're going to do one of the biggest derivative rules that you'll have all year. We used it twice last hour in Calc 2. The chain rule is huge. We're going to do the easy part of it today, so you won't get to see how rigorous it can be yet, but just the basics of it today. So the chain rule allows you to take the derivative of composite functions like f of g of h of x. And you can have as many as you want embedded. And it becomes kind of like the game Mousetrap, which looks like it would be fun, but it just, have you ever played Mousetrap? Do you own Mousetrap? It just never works. It seems like the game like, oh, that'd be so fun, and then you get it for Christmas and you set it up and nothing works. But the way it's supposed to work is that there's a chain reaction of events that as you turn the crank at A, it triggers an action at B, which triggers an action at C, which eventually drops the cage on the mouse. The problem is, if you actually have the game, it doesn't usually work, but theoretically, that's what's supposed to happen. And the chain rule is very similar in that you start a sequence of chain reactions, and Gottfried Leibniz is a German mathematician who he claims he invented calculus, but he just gave new notation to Newton's. Like Newton used to take the derivative and call it this. He used to call it y dot. Leibniz calls it y prime or dy dx, but it was already invented. He just put it in this, what we call Leibniz notation, the derivative of p with respect to a. And what happens is when I start at a, it triggers b, and then b triggers c, and then C triggers D, and then it triggers and it goes to G, and then it triggers and it goes all the way on out. And it's kind of like somebody earlier said, it's kind of like science where you have to do the unit analysis and get everything to cancel. When you're all done, you'll notice I have the change in P, what happened at P when I began at A. You know what I mean? And it looks really weird in this notation, but the theory is similar, that there's going to be a chain reaction of events, and that's why it's called the chain rule. It can go on forever if you wanted to, but we won't go past, like, I think the worst I make you do is a 5-linked chain. Not today. Today we get to 3. These are functions that don't require the chain rule. This would be power rule, derivative 2x. This would be trig rule, derivative is cosine x. This is power rule, the derivative is 3. This is trig and power. The derivative is 1 minus secant squared. Done. These are not chain reactions. But on this side over here, these are functions within a function. So this is the quadratic function embedded in a root function. This is 5x embedded in the sine function. This is a line embedded in a 7th degree polynomial. And so you can see these are of the form, go ahead and write it down, f of g of x. And that's when we use the chain rule. Before I tell you what it is, I'm going to have you go to the next page. And we're going to do one of them that you can do without it. And then I'll show you, I'll apply the chain rule to it. So right here with f of x being defined as 6x plus 5 quantity squared, you should be able to take the derivative of that. What would you do you think? Yeah, I would. I'd FOIL it out. So let's go do that. That we could do. So let's go FOIL it in our heads. 36x squared. Outside 30, inside 30x, combined for a 60x. Lasts of 25. So if I expanded that, I could just use my power rule. And no new info would be necessary. So when I power rule this, I'll get a 72x, bringing the power out front. I'll get a 60. The constant will go to 0. I may or may not notice that this factors, but let's factor it so you can see. The beauty of the chain rule is it gives you the answer factored, which is nice. This has actually got a 12 embedded in both terms. It would be a 6x plus 5. Now, that was all fine and dandy, and I think every 100% of you could do that correctly. But if I were to say to Jordan, Jordan, I want you to do the same thing, but I'm going to make the power to the 12th. We'd be waiting here for a long time. Do you see what he'd have to do? He would have had to FOIL, gotten this, then do this times 6x plus 5, don't write this down, by distributing all this in, write it down, then do a fourth one, distribute it all in, combine like terms, right? Do you see how crabby that would make him? You don't have to. The chain rule allows you to view this as a chain linked. You have a function within a function. And it says that you can pretend that this is just one chunk of stuff, like I'm going to call it u. If you were doing the derivative of u squared, what would you tell me it is? 2u. And it says to do that, just take the power, bring it out front, and say it's 2 times 6x plus 5. But then you have to go to the inner link, which is the 6x plus 5, and take its derivative. What's the derivative of 6x plus 5? 6. And you'll notice I get 12 times 6x plus 5. So I'm going to repeat what you do for the chain rule. You take the outermost function and you do that first. When that's done, you do the derivative of the inner function. I'm going to call that the derivative of the guts, but that allows me to tell Jordan to do this to the 12th, and he could probably do it in his head as long as the numbers don't get too big. It would be 12 times that stuff to what power? 11th. Okay, so he would say 12 times this stuff to the 11th power times the derivative of that stuff, which is what? 6, it'd be 72 times 6x plus 5 to the 11th. It would be the factored condensed version of if I waited 20 minutes for him to expand it all out. It's glorious. It's beautiful. You're going to do it quite well. You're going to not understand the notation at first, and we're going to work on that. Although this morning they did pretty well on understanding the notation. But this is actually going to be a big deal for us eventually. I'm not going to focus on this a whole lot. I want you to be able to use the chain rule. Then we'll worry more on the notation, but I'm going to give you a little flavor of what this is saying. It's saying exactly what I told you. So go over to this. You can do the chain rule in your head. You pretend this is just a chunk of stuff, this 3x right here, and you just ignore it. What's the derivative of sine? You write cosine 3x, and then you go times the derivative of the guts. What's the derivative of 3x? 3. That's answer right there. The derivative, go over here and write it. The derivative is going to be cosine 3x times 3. It's as easy as that. However, the notation for it is going to eventually be really important, so I'm going to give you a little dabble in it right now. This is saying that if you were to call this u, like the innermost function, this is saying to get the derivative with respect to x, you're going to consider it as, again, a chain reaction. You're going to take the derivative of that function with respect to u. What's the derivative of sine u? Cosine u. So you're going to write cosine 3x, which is what we did. But then you're going to have to do du dx to get the canceling to go. What is the derivative of 3x? 3. That's the formal notation. This is super important when we get to the real world problems because they're going to give you perhaps problems with something leaking. And they'll say, what? Don't write this down. What's the rate that the volume is changing over time? And maybe you'll say, well, I know that how the volume is changing with respect to the radius. I can figure that out. And then you'll say, well, but they gave us how the radius is changing over time. Well, then you have how the volume. You see what I mean? When we get to the word problems, it's going to be like, I liked how somebody in my morning said it's like unit analysis from science because it's going to be very similar. What you want your answer to be in, you need to keep it. But today, we're going to primarily work with can you crank it out. This is the notation that we're going to use more today. We're going to find the outermost function. We're going to take its derivative and leave the guts intact. Think of g as being the guts. What's g? The guts. And then you're going to do the derivative of the guts, and you'll be very successful. That's my goal today. So let's go on here. It says it's like unpacking boxes. It really is. You need to do the outermost one first, then the innermost. So with these right here, I'm going to do them on the next page. The goal is really to figure out which function to work with first. So this is a composite function. It is x squared minus 1 embedded in the root. However, you might want to write that as a power so you have better luck working with it. That's really what it is. So who is the outer function? The half. So you're going to ignore this. The book will say pretend it's u and just do its derivative with respect to u. You would do 1/2 of it to what power? Yes, thank you. Negative 1/2. That is f prime of g of x. I left the guts intact. I just dealt with the outer function. But then I multiply it by the derivative of the guts, which the book will call du dx, or they'll call it g prime. I'm going to call it the derivative of the guts to get you good at doing it. All right? What are the derivative of the guts? 2x. You're going to cancel the 2's. You're going to leave the x on the top because it's positive exponent. You're going to drop x squared minus 1 down as a root, and you have just done the chain rule. The chain rule can be done in your head a lot of times. For example, on this one, letter B, you're going to ignore the guts, and you're going to do the derivative of the outside function. What's the derivative of sine? Cosine. So you're going to write cosine 5x. That's what the book calls f prime of g of x times the derivative of the guts. What's the derivative of the guts? I'm done. What do you think? Pretty doable? Let's go to the next one. Do that one on your own. Until today, if I asked Maddie O to go do this one, she would have had to FOIL, then another one, then another one, then another one, distribute, combine like terms. It'd take forever. That can be done in your head, right? With the chain rule. Go ahead and do it. Pop up a hand when you have it done. I got 1, 2, 3, 4, 5, 6. Your hand was up second, Emily. I want you to tell me what you did. She did 7. To the 6th though, right? Yeah, so this is her viewing this as just an inside function. She did 7 it to the 6th. Then she has to do what the book calls either du dx or g prime, but really it's the derivative of the guts, which is just a 3. Your answer should have been 21, 3x minus 6, 2 to the 6th. How many of you had that, just out of curiosity? Awesome. So we're going to move right along here. Now, there's a huge difference. Be careful right here. And if you have a little room maybe off to the side, I want you to write these two things down and be very, 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 very careful with how different they are. For the one on the left right here, what is the inside function? X squared. So this one would be, okay, what's the derivative of sine? It's cosine, leave the guts intact, times the derivative of the guts. The red is its derivative. Perfect. The one over here on the right is much different because this is really sine x being squared. When you have it embedded in there as a superscript, so who's the inside function for the one on the right? Sine x. So I actually have to view that as like u to the second power. I do 2 times it to the first power times the derivative of the guts. What's the derivative of sine? Cosine. Do you see how different my answers are just with one tiny, tiny, tiny change? So be very careful what the inside function is. So let's go to letter D. What is the derivative of x? 1. What is the inside function? This is a composition of function. Who's the inside function? X squared, right? Who's the outside function? Tangent. So I do the derivative of tangent first. What's tangent's derivative? Secant squared. Excellent. I leave the guts intact, or the inside function intact. The formal notation for that would be f prime of g of x is what I just did. I did the outer one's derivative, left the guts intact. Now I'm going to do the derivative of the guts. What's the derivative of these guts? 2x. Okay, so I would write times 2x, but then you'd usually put that out front for better syntax. It'd be 1 minus 2x secant squared, x squared. All right, letter E. You might be tempted to launch into the quotient rule and you'll get the right answer. But watch what happens when you do. You'd go low, D high. What's D high? 0. Anytime you're doing product or quotient rule and one of the parts of it is 0, it means there's probably a better, quicker way. And if I were to write this as x plus 1 to the negative 1, I don't have to view it as a quotient. I don't have to go low D high minus high D low, draw a line and square below. I've now got a function within a function. See what I mean? So I am going to take the derivative by ignoring the guts and just dealing with the power. I bring the power out front. I leave the guts intact. I drop the exponent 1. And now I do the derivative of the guts. What's the derivative of those guts? 1. But be careful, because don't write this in your notes. Had this been a 5, then that was a 5, then that was a 5, and what would be the derivative of my guts? 5. So although I get to kind of ignore it on this one because the derivative of the guts, or what the book calls G prime, is 1. My answer would be negative 1 over x plus 1 quantity squared. Last one. I, on letter F, have embedded 3 links into the chain. Or you can think of it 3 layers or 3 packed boxes. I've heard it being called like a peanut M&M where you have the shell and the chocolate and the nut in the middle. But you just really need to figure out which layer's which, and then you collapse in on it. So who do you think the outside function is on this? The squaring, thank you. Rewrite it so you can see that. You're really being asked to take the derivative of sine of 3x, all of it squared. It's just historically they made an agreement to put that in as a superscript so they could avoid having to write parentheses all the time. Do you see why they might have chose to do that? But you have to see it as outside. So I'm going to ignore all of these guts and just take the derivative. Anything squared. Bring the power out front, keep the guts intact, knock the power down 1, which would be to the first. But keep in mind, had that been a 12 right here, I would have put a little 11 in here. But I'm good. That was 1 layer. That's like the shell. The chocolate is the sine function. Do that first before you get to the nut, right? What's the derivative of sine? And just leave the guts intact. Leave that peanut right sitting in the middle. It's in the middle of all of it, right? And then the derivative of the very inner guts is what? 3. So you'd multiply the whole thing times 3, and then you'd make it 6 sine 3x cosine 3x. What do we think? If someone was absent, do you think you could teach this to them? Could you do it on your own? I think so. Let's go take a look and go try this one on your own. Raise your hand when you have it. This would be what I call a level 1 problem. I would hope everybody gets this one right. Then I'm going to do a level 3. We won't get to level 4 and 5 till Monday. They do get a little more complicated, but go ahead, raise your hand when you're done. I got 1. Pop up hand 2, 3, 4, 5, 6. Okay, there we go. There went the most of you. So let's go see how you did. Again, whoopsie, you are viewing this right here as just its own function. You don't put a u there. I actually think the notation kind of muddles the issue. We do need to be good at it eventually, but for now, I just want you to take the 3, bring it out front, leave the guts intact, right? Drop it down, and then what? Derivative of the guts. Derivative of the guts would just be 14x minus 25 x to the 4th, right? And you can just leave it. How many of you had that right? Tons. Awesome. All right, now let's go to a level 3, not a 4. I mean, here's why this one's going to be a little tricky. First of all, how many layers are there to this? How many links in the chain? There are 3. What are they? Squaring function, cosecant function, Linear function, right? So who's the outside function? Awesome. It's the squaring. So let's rewrite that so we can see it. We've got cosecant 7x minus 1, and that whole angle is being squared. I didn't do anything except make it so I could see each individual layer, and then you collapse in on it from the shell on in. So you're going to ignore what this is. Who cares? Maybe it's w. Doesn't matter. A function squared or something squared, its derivative is 2it to the first. It's just when it's an entire function, not just x, we have to do more to it. But I'm going to take the 2, I'm going to leave cosecant intact. The whole thing, I'm going to drop it down to the first power, which isn't really necessary, so I'm going to erase it. That's the first link. The second link is the what function? Cosecant. You might have forgotten its derivative, which makes this a little more difficult. You have a chart in your notes, but I'm going to see if you can think it out. You haven't used it much, so odds are maybe not. But I told you to eventually try to remember the derivative of secant. Do you remember what it is? Derivative of secant is secant tangent. Okay, now that one you're eventually going to have to get in your memory. Until you do, look it up, but get it there eventually. Cosecants, if you remember I made that chart, it's almost identical. But do you remember there's one minor difference for the cofunctions? They were negative. All of their derivatives were. So the derivative of cosecant of anything is negative. I'm going to throw it out front so it doesn't look like subtraction. Negative cosecant it times cotangent it, but because it is a function itself, I still have another layer, right, Abby? What's the derivative of the innermost function? 7, exactly. So this whole thing would be times 7, which if we were to write it nicely, we would write negative 14. We have 2 cosecants, so you'd write cosecant squared 7x minus 1, and you would clean that up a little bit, give it a little bit of a facelift. So the last one of these, and then we're going to see if you kind of have the notation down. How many layers are there to f? I think in Algebra 2, it used to be that they would give you something like this and they'd tell you to decide, they'd say this is f of g of h of x. Tell us who each is. Did you ever have to do that? And you'd say, oh, f of x is the square root of x. G of x is tangent x, and h of x is 6x squared minus. That's kind of what I'm asking you. It's that same thought process. The outermost function on this is really a power function. What function? What power? Yeah, there's a 1/2 really embedding the other two functions, or they are embedded in it. So what am I going to do first? Go ahead and tell me, Joe. What would I do first to take the derivative of f? I'm going to change colors here. Let's just pretend that, okay, let's go. Suppose I said this. What's the derivative of that? Go ahead, tell me, Joe. Yeah. And then drop it. I'm going to do the same thing. I'm going to put the 1/2 in front. I'm going to keep all of these two inner layers intact. I'm not touching the chocolate or touching the peanut till I get the shell taken care of. It's a stupid analogy, but it's kind of works for me. All right. This would all be to what power? -1/2. Now, because you're writing it and you don't need to use it, instead of bracketing and going to the -1/2, maybe you want to write it in here. Doesn't really matter, but you better put some parentheses if you don't do that. But because I'm subscripting it, or superscripting it, sorry, I'm going to remove these. All right, I just did only the shell. Now do the chocolate. Who's the next layer in this embedment? Is that a word, embedment? Tangent. What's tangent's derivative? Secant squared. There it is. So I'm going to do secant squared. I'm going to keep the guts intact. Who's the innermost layer? There it is. What's its derivative? 12x. It looks way harder than it is, which is generally the case with calculus. If your parents were to watch you do this, they'd be like, oh my God, that looks really hard. But it's really not when you pick it apart. I would probably put this with the 1/2 and call it a 6x, What else would I probably do were I to actually write it as my best answer? Yeah, get rid of the negative by putting the tangent function on the bottom under a root, probably. All right, so I told you I'm not super concerned about the notation yet, but I'm eventually going to be very concerned about it. And let's see if you kind of get it right now. You'll have it eventually, but this is how you will be tested on peer theory, which for some people, if they get it, these are easy questions because you don't have to do all the manipulating and the algebra of it. It's just peer, do you understand the chain rule? First of all, what rule would you apply to this to find the derivative? This is product rule. You would do first d second plus second d first at 2. We already know how to do that. What rule would you apply to number 17? Quotient. You would do low d high minus high d low. You would draw a line and square below at 2. Now we're going to add a new one. This is a function, f of x. I don't know what it is. It might be sine of 8 million x. I don't know. But it's a function embedded in the cubed function. So when I do its derivative, it would be 3 times f of x squared. And that's what most kids would do, and it'd be wrong. Because what did I forget? The guts, right? And the derivative of those guts, whatever they might be, would be called f prime of x. You don't actually have to go take it. They're going to hand it to you. It'd be 3 times f of, they want you to use a 2, so they'll go hand you f of 2 right here, negative 3 squared, right? Times f prime at 2, which they're going to hand you on a platter, and you just go do the arithmetic. So last one of the day. Number 19. Many kids would launch into the product rule because they see this. If you were to read what number 19 is, what would you say? F of, that's a chain rule. Which function would you take the derivative of first, f or g, at the outer layer? So you do f prime. What would you do with the guts? Keep them. Leave them intact. Do not touch the middle layer until you've taken care of the derivative of the outer layer. See what I mean? That means you understand the model. You do f prime of g of x times what? The derivative of the guts. And so we're calling it the guts, which is nice because the book usually calls it g and they kind of go together, hence the reason. Now, this would normally be multiple choice, and let me tell you what College Board will do. They will do the product rule on this with 2 and have that be one of them because they know some kids are going to do that. They're going to see that as f times g. They're also going to do, let's go put in a 2 right here. Do you think some kids would just do f prime of g of 2? That will be sitting there then. So let's go, g of 2 is 3. F prime of 3 is 4. So this right here is 4. Many kids nationwide will forget about those guts, and they'll circle 4 and they'll think they did great, right? But I need to multiply it by g prime, the derivative of the guts, which they handed to me, which is nice, right? What is the correct answer? Negative 8. All right, so I'm going to give you the worksheet. If you are absent and you're listening to this and you didn't pick up a worksheet, I am going to attach the PDF into Schoology. This is due Monday. You'll start it when you're done with your quiz. It's nice, and this is about a 15-minute ordeal. It's nothing like 1 through 53 odd, which was a necessary evil. This one you don't need to do a whole lot to be. This is pretty straightforward stuff. So this assignment, actually I had some people get half of it done after their quiz even. Takes you a total about 10-15 minutes. Do it sometime by when? Monday. All right, I'm going to pause this and